Okay, so let's try and make the connection between physics and calculus. So if you've done integrals before and you know maybe a little bit about differential equations, this might make more sense to you. If you haven't, then this video might not make sense to you at all. But if you have, then we can make a connection here in the sense that we can actually derive two of the kinematic equations using calculus. And if you recall, the kinematic equations are they're derived under the premise that acceleration is constant, right? So that's the premise. So acceleration usually it's going to be negative g, so that's 9.81 meters per second squared. Acceleration is just constant. What that means is that when you have a position time graph of an object in motion, it's going to appear as a quadratic curve, so to speak, right? It's a curve such that when you differentiate it, right, with respect to time, you get a velocity time graph, right? And that's going to be linear. And then when you differentiate that with respect to time, you're actually going to get a constant linear graph, right? And that is what we mean when we say acceleration is constant. It does not change. It just keeps going. As time increases for any point in time, the acceleration is the same. That is what we mean when we say the acceleration is constant. Now, we can actually use some integral techniques to just derive the first kinematic equation, then we can use that to derive the second one. So here's what I mean. If we multiply both sides here by dt, right, and acceleration is defined as the derivative of velocity with respect to time, right? So let's try and manipulate this equation here. And if we do this, right, these dt cancel out, and we're left with the differential form. And you'll see why I do this, because then we can integrate. So we'll have acceleration dt dv, like so. Just going to move this down there. And now we can integrate both sides. Remember, your bounds have to be in terms of the same variable that you're integrating with respect to. So it's going to be the integral of acceleration from t1 to t2, and the integral of the velocity differential from v1 to v2, like so. Now, because we said that acceleration is constant, right, we can actually just pull this acceleration out of the integral. And we can do that because that's one of the properties of an integral. You can actually pull constants out. So when we do that, we're left with the acceleration times the integral from t1 to t2 of the time differential is equal to the integral of the velocity differential. What's the integral of the velocity differential? It's just velocity, right? It's the difference in velocity, the full difference, right? The dv is a little bit of velocity, and the integral essentially means the summation of all those little bits of velocity over some interval. So that's just the entire difference in simple terms. So we're just going to have delta v, right? And now what we can do is we have the same case here where it's, this should be t1, sorry. It's the integral of the time differential, and that's just going to be delta t. So we can just put delta t like so. And now we have something that looks a little more familiar. This is acceleration is equal to delta v all over delta t. What does this say? We kind of just got exactly what we had before, sort of, but now it's in delta form, so to speak. What it means is that the instantaneous acceleration is actually the same as the average acceleration, right? So this is average, and then this is instantaneous. And that makes sense. Think about it. It makes sense because when you have the acceleration graph here, the average acceleration is just the average acceleration from this point to this point. But if you have an instantaneous acceleration at any point, it's actually just the same at any given point. So the average acceleration is the same as the instantaneous. So that's why we can write dv over dt as delta v over delta t. And now we could sort of rewrite this a little bit. in a form that's more familiar. So Vf minus Vi delta t, like so. And we can write delta t as just 1t if you'd like, because yes, the delta t is equal to t f minus ti, like so. But if we let ti equal to 0, as in we start at the origin of our graphs here, then we can just let it be tf, the final time, and we can just call that t, like so. Just an easier form of notation, that's all. And because acceleration is just a constant, no matter what the time is, we don't need to write it as a function a of t, we can actually just write it as a. So what we have finally is velocity Vf, so we're going to move this, we're going to multiply t by a, like so, and then we're going to add Vi, so initial velocity up front, like so. And just rewrote in this way so it's a little more familiar to you. That is the kinematic equation, right? Now, I'm going to rewrite this a little more just to make it make sense later on. When we have this equation, right, when we write it in terms of Vf, Vf is usually the thing that we want to find, right? So we can actually make it, we can actually write it as a function, right? I've not changed anything, it's still the same equation, but I want you to see that this equation is useful as a function in and of itself. So if you want to find a particular velocity at some point, right, in time, right, then just find the time. You'll probably be given the time, and then you can just plug it in to this function, and then you'll get the velocity, right? So I want you to think of it as a function, right? It varies with time. And this is going to be useful in our next derivation. So here we start with the definition of velocity, where it's equal to the derivative of displacement with respect to time, right? Let's do the same thing where we just multiply by dt on both sides just to cancel these out, and then we get the differential form. So we're going to have v of t dt is equal to dx, like so. And then we just integrate both sides, just like we did before. And we're going to do it with respect to the bounds have to be the same variable, right, as the variable that you're integrating with respect to. So it's going to be from t1 to t2. And on this side, it's going to be from x1 to x2, like so. Okay? And so what we can do now is try and figure out this integral, right? So we have v of t. So, and this is, I want to bring you back to this equation, and this is why I told you to write this as a function, right? Because when we start integrating by over here, we're integrating a function, right? And we can actually substitute this right side of the equation, right? This right side of the equation, highlight that in blue, and we can actually just put it right there, right? And this is better because we didn't define the initial velocity as a function, and a is just a constant, and time is the only variable here. And we're integrating with respect to time, that's going to make our integral a lot easier. So if we make this substitution, the integral becomes possible. So let's do that. So v of t is equal to initial velocity plus acceleration times time. So it's going to be the integral from t1 to t2 of initial velocity plus acceleration times time dt is equal to, what's this? So this is the integral of the position or displacement differential, and that's just the entire difference, so delta x. So dx turns to delta x, right? So that's what we have so far. So we have a, we can actually separate this integral. So what we can do is the integral from t1 to t2 of initial velocity with respect to time plus the integral from t1 to t2 of at dt is equal to delta x. So things might get a little harder to see, but I'd like you to notice that the acceleration, remember that it's a constant, we can actually just pull this out, right? And then we're just left with the time variable, which we can integrate very easily. And on the left side here, we have the initial velocity. Remember, we defined it as a constant, right? We look at the final velocity as a function, but the initial is a constant. It's assumed that you already know it. So because of that, we can actually pull this out as well. So here's what we have. We have VI, the integral from t2 to t1 dt plus a, the integral from t1 to t2 of t dt is equal to delta x, like so. Okay, so now here we have the same case where the differential is being integrated, and that's just the delta. So that's going to be vi delta time, delta t, plus acceleration times, what is this? So, right, so what is that? So that's going to be the integral of time is just going to be t, 1 plus the power divided by that sum of the power. So it's going to be, so this is to the power of 1, it's going to be to the power of 2. So we're going to have t to the power of 2, and then we multiply by the reciprocal of that new power. So it's going to be 1/2, like this. Okay? Okay. And then that is equal to delta x. Do a little rearranging. We know that delta x is just x final minus x initial, like so. We can rearrange for xf, like so. xf is equal to xi plus initial velocity times time. If we set t1 equal to 0, we can just call this time, right? So time plus 1/2 at squared, like so. And that's our second kinematic equation. Thank you for watching, and I'll see you back again next time.